Okay, yesterday we were working on a particle moving, so we're going to model this as a particle, and that's one of our sort of assumptions, is we're going to model as a particle. That reduces all the forces down to things like friction. So I'm going to say friction's moving backwards, because if you look at the other forces, we're attempting to move right. Okay? This friction, until you know where you're trying to move to, you don't know which way friction is going to work. So the friction is moving right for our thrust. So the thrust tries to move us this way. Friction acts against that movement. We've got our weight, which is 49 newtons. In a minute we'll come back why this was here. And we've got the reaction of the surface. And that reaction should also be linked over here to the mu. So reaction causes friction. At the moment you just need to know they cause them. The next chapter links those together. The table, because we're not moving vertically, there is no vertical component. So what we actually have is we now actually have an imbalance. So we're not in equilibrium. That means we are going to cause some form of change in motion. And the change in motion is actually the force, the net force, or the resultant force leads to acceleration. And if you understand Newton's second law, or recognize this as Newton's second law, I might as well say Newton on the front, because this was one of his big additions. Newton's second law is the force is equal to the mass times the acceleration. Mass is just a scalar quantity, but the force is a vector and acceleration is a vector. So we've actually got both vector and scalar relationship here. So we can actually now go in and actually work out what's actually going to happen to this particle. Now, there is a second thing that is worth noting here, that the force due to weight, again, is a force. So the weight is actually a force from the mass times some acceleration. And the acceleration is gravity. If we were to not have a table here, it would accelerate as it's pulled by the Earth. So normally we take gravity as 9.8. We've got 49 as the newtons, we've got our mass, and gravity is 9.8 meters per second squared. So my mass is 5 kilograms. Okay, so that's the mass that's being generated. And this force is the resulting force. So I'm going to turn this into a vector diagram. It's not a bad one, because you'll notice very quickly that the j and I, in the j direction, everything balances, because we've got no acceleration in that direction. So we can actually say the resulting force is equal to our weight component plus the reaction plus the thrust plus the friction, or, and these are as vectors, or you can resolve them directly, or you can say force in the j direction is the weight, or negative weight, plus our reaction force. And because these two are equal, 49 newtons down plus 49 newtons up, this becomes 0 newtons. And resolve in the y direction, we have thrust minus the friction. So the first minus friction is 10 newtons minus 5 newtons, which is 5 newtons overall. The vector version above, our resulting friction force has an A and a B component. The weight is a minus 49 newtons. The reaction is a plus 49 newtons. My thrust is 10 in the positive direction, and the friction is 5 in the negative direction. So these two things are equivalent, and that's why that can happen together. So what's this net result lead to? So what actually happens is the reaction, the resulting force is equal to the mass times the acceleration. We made a note over here that weight is 9.8 g times the mass. So the mass, we can actually go 5 newtons is 5 kilograms times our acceleration. So the acceleration is 1 meter per second squared in the positive I direction. And we're going to accelerate at that speed. Sorts of things that might come up from this. Now, I wouldn't write anywhere near as much of this as I have done. We'll do another problem in a minute. But a follow-on question to this might be, how far does a stationary block travel in, let's say 2 seconds. And we now have an A. We think about our situation. We've got U is 0. Acceleration that we now know is 1. And we know it's going over time t, so we've got smooth out. We know the acceleration, we know the time, we know the initial velocity is 0, and that's what we want to work out. So the equation is S equals ut. So all of this should have been done in different colour so that we can see how they work. S equals ut, add on 1/2, at squared, and we put our values in. We've got 0 times t, which is 2 seconds, plus 1/2 times 1 times 2 squared. So the distance it will cover in that time is 2 meters.